Yeah. Yes.
So, hello everyone. We are Team Banyanya, and today we are going to give a presentation about what we have achieved. So, the team consists of my friend Yunsheng here and me, Wei Jin. So, firstly, give a short explanation about the attack we have used, which is the HopSkipJump attack. After that, we'll go through the successful attack attempts on other teams, and finally, the changes that we have made to the HopSkipJump attack. Adversarial attacks were first observed by Sagatti in 2013. So when a perturbation is applied to a correctly classified image like this panda right here, the neural network would misclassify the image as a gibbon. So the perturbation applied is often unrecognizable to the human eye. The emergence of adversarial examples brings huge security risks to a system based on deep learning models, such as automatic driving and face recognition systems. Hence, it has been widely concerned by academia and the industry. So, the most important criteria when grouping adversarial attacks is by their threat models. There are three kinds of threat models. So a white box threat model assumes access to the whole model. A score-based threat model assumes access to the output layer, and a decision-based threat model assumes access to the prediction label alone. So in this presentation, we'll focus on the decision-based setting. Adversarial attacks can be also grouped by their attack objective. So untargeted attacks can be defined as the following optimization problem, where we aim to minimize the distance between the perturbed image X prime with the corresponding original image X, subject to the constraint that the label of the perturbed image is different from the original image. The targeted attack aims to minimize the distance subject to the constraint that the label of the perturbed image is a given target class C star. So before we go into detail about the algorithm, we first define an important concept, the boundary of targeted and untargeted attack. In the untargeted setting, the boundary function S is defined as the maximum probability of the rest of the class minus the probability of the original class. In the targeted setting, the boundary function is defined as the probability of the target class minus the maximum probability of the rest of the classes. The definition of the boundary function S implies S is larger than 0 if then only if the model retrieves maximum probability at the wrong class in the untargeted setting and the target class at the targeted setting. S is positive if and only if the attack is successful at the boundary is defined as the set where S is 0. The objective can now be written into a representation, minimizing a certain distance matrix subject to the constraint that the boundary function S is positive. So now we'll move on to the algorithm used in the HopSkipJump attack. So HopSkipJump attack uses an iterative algorithm where each iteration consists of two steps, the boundary search and the gradient update. So on this figure, the blue region is where S is positive, and the red region is where S is negative. X is the original image, which lies in the negative region. So assume we start from X to the T in the positive region. We first do a binary search on the line connecting X to the T and X to find the intersection with the boundary XT. In the second step, we compute the gradient at XT, which we then update XT with a pre-chosen step size, which is decreased until the updated point X to the T plus 1 lies in the blue region. Then we do another binary search to find XT plus 1. So these steps are carried out iteratively until it converges. Now we'll talk about the teams that we have attacked successfully. So we have targeted the team light dot projected downfall, The topic suggests that the existence of adversarial attacks may be an inherent weakness of deep learning models. With this in mind, they study the adversarial robustness of neural networks through the lens of robust optimization in order to train networks with significantly improved resistance to a wide range of adversarial attacks. So in their Google Colab, they have used the MATRIS generative adversarial networks. So we bypass their defense by using spatially transformed adversarial images. So this is done by changing the position of pixels instead of directly manipulating existing pixel values. This method has been shown to better preserve the identity and structure of the original image. So this is an example of the attack. On the left is the original image where the model predicted it to be 0. So after we have spatially transformed the image, which can be seen on the right, the model predicted the adversarial image to be 9. So we have tested the attack with a total of 101 images with a success rate of 90%. Now I'll pass it to Yunsheng to talk about the changes we have made to the HopSkipJump attack.
Thank you, Wei Jin. Now I would like to talk about what changes have been made to our Google Colab. So our team that found out that the binary search used in HopSkipJump is not as efficient as we thought it would be. For each iteration, the upper bound will be set as 1 and the lower bound will be set as 0. Both of the graphs show the final result of the binary search in each iteration. As you can see, the final point usually reach around 0.7 and 0.8 and 0.9 for both untargeted and targeted attack. For milestone 2, we have developed an improved search, which is a 70-30 search. Since we understand that the final value in each iteration is very high, we skew the bias towards the higher points. Hence the introduction of the improved search. So how does it work, you may ask? Instead of calculating the mean point by adding the upper bound and lower bound and divide it by 2, we can calculate the middle point by using the 30% of the upper bound. We can visualize it with the diagram below. The binary search can go up to 0.75 within 2 iterations. As for the improved search, it can go up to 0.91 within 2 iterations. This can help to improve the number of iterations of the HopSkipJump attack. Here are the results. As you can see, we improved the efficiency by around 5%. Even though the result reflected that there is efficiency improved, is it good enough? With the suggestion given by Dr. Raphael in the milestone 2, we look into the internet to find a better search algorithm. We can combine jump search and binary search at the start of each iteration. We can first use jump search to find an initial lower boundary. After that, we can continue to use binary search to search the boundary point. Let's look at some example. Let's assume the jump search is decreased by 0.1 in each iteration. The first iteration, the attack was successful. The second iteration, the attack was also successful. This will be continued until the attack fail. This means that the boundary point lies within the range 1 and 0.6. The attack was better than I expected. As you can see from the graph, for untargeted attack, the average efficiency increased by 90%. For targeted attack, the average efficiency increased by 22%. Now we look at some demo. As you can see, for untargeted, initially the classifier classified this as a sidewinder, which is a type of snake. After the untargeted attack, the classifier now classify this as a hawk-nosed snake, which is another type of snake. We have tested the untargeted attack with 100 data set, as you can see here. You can open each cell for 10 images to check the result, the initial image and the result. For targeted attack, we first define the initial image as a tractor. Then we find a target image, which is the sidewinder. Then we change the image. We apply the HopSkipJump targeted attack. As a result, the classifier now see this as a tractor instead of a sidewinder. Similar to targeted attack, we also try this with 100 image, as you can see here. And we have split it into 10 image itself, where you can open it up and see the result. And this is the result over 100 images. That is all for our slide. That is all for our presentation. Thank you very much.